Hello everyone and welcome to the presentation of the paper titled A Cosimulation Methodology for Offshore Load Handling. My name is Sabin Vishwanathan. I am a postdoctoral researcher at the Department of Mechanical and Industrial Engineering at NTNU. My co-authors are Associate Professor Satish Babu from the Department of Ship Technology at CUSAT, Associate Professor Christian Holden from NTNU, and Professor Olav Egeland from NTNU. We will begin the presentation by talking about offshore load handling. We will look at the limitations of conventional load handling simulations. We will then introduce the cosimulation methodology. We will look at the modeling of the electro-hydraulic winch drive, followed by the modeling of the offshore support vessel with the A-frame and the payload. We will then discuss the results of the cosimulation and draw our conclusions. Load handling is one of the most frequently carried out ocean engineering operation. In the figure that appeared on the screen right now, we see a payload suspended from an A-frame mounted on an offshore support vessel. The payload can be lowered or raised using a winch. The winch is not visible in the photo. In the photo that appeared below, we see a knuckle boom crane handling a payload in a ship-to-ship transfer operation. And in the figure that appeared to the right, we see a fully assembled wind turbine being installed on its jacket foundation by using a crane barge. Offshore load handling is generally divided into two categories, a light lift and a heavy lift. In a light lift operation, the mass of the payload is generally less than 1 to 2% of the displacement of the vessel. The dynamics of the mass has no significant impact on the dynamics of the vessel itself, and so we can use the displacement response amplitude operators for specifying the platform motion. Whereas in the heavy lift, the payload mass is generally greater than 1 to 2% of the vessel displacement. The dynamics of the mass has a significant impact on the dynamics of the vessel itself, and so we need to use the load response amplitude operators to determine platform motion. In the work presented in this paper, we will be looking at light lift scenarios. Simulation of offshore load handling operations can be carried out using software like OrcaFlex, where the control variables are the length of the winch wire, the tension in the winch wire, as well as the position of the constraints which model the linkages of the crane. This means that we can carry out simulations involving the raising and the lowering of the payload while accounting for the effects of the change in the orientation of the linkages of the crane. However, we observe that there is a lack of component models which enable the modeling of the drive of the load handling system, and hence there is a lack of simulation output pertaining to the dynamic response of the drive of the load handling system. In some scenarios, for example, if you are a designer of such offshore load handling systems, you are interested to know how the drive of the system responds to various external factors. And this is the basic motivation behind the work presented in the paper, where we try to couple the dynamics of the drive of the load handling system, the drive being modeled in a Modelica based software like Simulation X, with the dynamics of the load and the vessel, which are modeled in OrcaFlex. And the one factor that makes this possible is that the winch wire length or tension can be specified using an external function in OrcaFlex. And so in the cosimulation methodology that we present in the paper, we model the drive of the winch in a Modelica based software called Simulation X. We model the vessel as well as the A-frame and the suspended load in OrcaFlex, and we couple the response of both these systems using an API interface. We now look at the subsystem models of the cosimulation model. First, we look at the model of the hydraulic winch. We see a hydraulic pump driven by a constant RPM constraint in Simulation X. We could have replaced this constant RPM constraint with the component model for an electric motor, which is already available in Simulation X library. but for reasons of simplicity, we limit ourselves to a simpler constant RPM drive. The hydraulic pump pumps hydraulic fluid through a 4x3 proportional direction control valve into a hydraulic motor, which is coupled to the winch drum through a reduction gearbox. A function called lever position controls the spool position of the valve and thus emulates operator input. Depending on the spool position, the hydraulic fluid either flows from port B to port A of the hydraulic motor, lowering the load, or from port A to port B, raising the load, or if the spool is at the center position, then all the ports are blocked and the drum of the winch is blocked. We also have a bypass valve which allows for the bypass of the hydraulic fluid when the valve is at the center position. We also have pressure gauges to monitor the pressure at the various hydraulic lines. The component model for the winch is already available in Simulation X, along with component models to model the winch wire as well as the pulleys. All these functions shown here are used for transferring the loads from the Octaflex model into the Simulation X model. So looking at the Octaflex model, we see that the vessel is modeled along with the A-frame, the payload, the winch wire and the pulley arrangement. And at each simulation time step, we pass on the load acting on the winch wire as the load acting at the tip of the winch wire in the Simulation X model. We then pass on the response of the Simulation X model in terms of the rate of change of the unwound wire length as the payout rate of the winch wire into the Octaflex model, and all this transfer is enabled using an API interface file coded in Python. The API interface file along with the Octaflex and Simulation X model files are available for download at the location specified in the paper. We now proceed to discussions of co-simulation results, and first we look at the calm water operation where the load is lowered, held constant at a specified depth and raised out of the water, all in the absence of waves and currents. The lever position is the operator input which controls the opening of the valve, which in turn controls the RPM of the hydraulic motor, which then dictates the RPM of the winch drum. We see that as the lever position is put to +1, the winch drum rotates with +8 RPM in the positive direction, and this lowers the load. As the lever position is brought to the 0 value, we see that the winch drum is locked at 0 RPM, and so the load is held constant at the predefined depth. And as the lever position is brought to -1, we see that the winch starts rotating in the negative direction, thus raising the load. If we look at the x directional response of the payload, we see that it remains constant because in the absence of waves and currents, the load drops down vertically as it is lowered and raised. Looking at the system pressures, we see a corresponding response. As the valve is opened at the beginning of the simulation, we see that the system pressure drops to a constant value. It then continues at that constant value until the load begins entering the fluid domain. As the load enters the fluid domain, buoyancy acts on the load and this reduces the weight pulling on the winch drum, and this raises the system pressure slightly. As it is fully submerged, the pressure remains constant, and once it reaches the predetermined depth and the valve is closed, we see that the pressure climbs to 400 bar. At 400 bar, the bypass valve opens, and so the 400 bar pressure is maintained in the system. Again, as the valve is opened in the negative direction, we see that the system pressure drops. It continues at a constant value until the load begins emerging from the water, and now the full weight of the load acts on the winch drum, and again we see a slight increase in the system pressure. We also notice that the system pressure in the lowering phase is slightly lower than the system pressure in the raising phase, because here you are acting in the direction of gravity, and gravity is actually assisting the the lowering of the load, while here you're acting against gravity, and so this causes this small difference in the lowering and the raising pressures. Similar explanations can be given for pressures P3 and P2. Looking at the winch wire tension, we see again a corresponding response. The winch wire tension is higher when the load is suspended in air. As it begins its journey into the fluid domain, buoyancy starts acting and the winch wire tension reduces. It then continues at that constant value until it is raised out of the water, at which point the winch wire re-attains the initial value. We now look at the results of the offshore load handling operation carried out in the presence of waves. The operator input, the spool opening and the response of the hydraulic motor remains the same. What we notice is the influence of the waves on the kinematics of the payload. The waviness is because the vessel is now responding to the waves. And if we look at the x-directional response, we see that the amplitude of the response is higher as the payload enters and exits the fluid domain. This is because the wave-induced water particle velocity is higher near the surface, and so the drag is higher near the surface, and this causes the load to oscillate with a higher amplitude as it enters or exits the fluid domain. The effects of the dynamic amplification of the load is reflected in the system pressures as well as in the winch wire tension. And this brings us to the close of the discussion of the results. We now proceed on to our conclusions. First, we see that Cosimulation makes available a whole range of results pertaining to the dynamics of the winch drive, which was otherwise not accessible using Orcaflex simulations alone. The results are seen to be in general agreement with the physics of the system. Cosimulation opens up the possibility to test controllers and carry out hardware in the loop simulations, because Simulation X supports hardware in the loop simulation, and the Modelica library has component models to model various electronic and electrical components. The cosimulation methodology may be extended to other scenarios, for example, in the analysis of short tension mooring systems or top tension riser analysis. However, cosimulation is time consuming, and hence standalone simulations using Modelica software may be investigated. This would require the development of domain specific component models, which are not already available in the Modelica library. Validation of the simulation results is pending. The major factor for this is the dearth of field data pertaining to offshore load handling operations. However, we are in talks with the industry to source such data, and as this becomes available, we hope that the results can be validated. And that brings us to the close of this presentation. Thank you. And if you have any questions, please feel free to ask.